Okay, thank you. Like has already been said, we're two architects working at Piksel. My name is Paul Wilson. This is Stephen Gran, and what we want to talk about today is Mesos and container schedulers, particularly for people that are evaluating Mesos, thinking about how to more efficiently schedule their workloads, different types of workloads that you can run on Mesos, and some of our experiences as we've kind of learned and evolved our infrastructure to better manage our workload types.
So Pixels, we've been around for about 20 years. Can you hear me? Is this on? Fair enough. We've been around for about 20 years, working with a lot of large providers in the online video space. Should it be better like that, is what you're saying? Can you hear better? Yeah. Okay. So these are some of our current and past customers. Most of our work with them has been building bespoke video solutions for them. So they'd come to us with a problem and we would solve it for them. About 3 years ago, we decided to build our own SaaS platform that we could resell to multiple customers and provide a better solution overall to all of our customers. So what we're talking about today is the platform underpinning our SaaS video platform. So
as you can see, these are the sort of tool sets that we've decided to build that platform on top of, and as you can tell, we're big fans of the Apache tool set. Most of these things come from the Apache suite of open source software solutions and predominantly out of the big data space.
So this is a sample application workflow that ties together a bunch of these software stacks to deliver on a customer need. In this case, we're doing automatic enrichment of video metadata.
Yeah, so a user would interact with our API services. That would result in writes to Cassandra. We then have a firehose change data capture, writing to Kafka, which we then have offline sort of Flink processing, doing background enrichment, analytics, and other kinds of interesting stream processing off the back of those writes to Cassandra, and then ultimately back to Kafka and then back into Cassandra again.
So what we want to talk about here is our journey from beginning as a kind of a classic run everything on a bunch of virtual machines towards having a unified managed data center that we can treat as a single operating system providing us a pool of resource. We want to talk about some of the primary benefits, the things that moved us towards making this decision, but also about the secondary benefits, the way that this changed how we work on software and how we deliver that software. Things that maybe they weren't unexpected, but they weren't the reason we invested in this, but they've had equally transformative effects on our delivery.
So going back maybe 2 years now, this is what our platform looked like from a kind of infrastructure perspective. We describe this as static partitioning. We have a set of VMs with the different colors there, and they are provisioned to provide different services within the platform. So we have a suite of web services, some messaging, some ESB, some DB. It's the classical sort of Puppet-based provisioned platform with auto-scaling groups, etc. But the key point is each VM is provisioned for a particular purpose. And this is static partitioning. And there's some real drawbacks to that model of infrastructure. And that is it's impossible to efficiently utilize all of the resources on the machine. So let's imagine you've got a big caching server. You need a lot of RAM for that, but you don't necessarily need the CPU. So some of the CPU utilization you're not using that CPU utilization efficiently and effectively. So you're not packing the applications tightly into the available resources on the machines.
And so you look at this problem, and one response might be that you could run 2 services on that machine. You'd run a RAM-heavy service, and you'd run a CPU-heavy service. But you run into problems there because those 2 applications have different scalability requirements. The operating system doesn't give you resource isolation guarantees that are strong enough to prevent the CPU-heavy application from swamping the response time of the memory-hungry application. So that ends up being a not very good response to the problem. And so this is what actually drove us to start looking into this for ourselves. This is after about 2 years of running on AWS. 500 VMs. 150 of these are relatively lightly used API services. It's a microservice architecture, so a few of the microservices are very busy. A lot of them are relatively idle. But the unit of provisioning in AWS is a CPU. So if you have 150 API servers, you have 150 CPUs you're paying for. And it was frankly just wasted money.
Yeah, I'm not sure if you can see at the back there, but we're running 500 EC2 instances at this point. Yeah, and another more subtle implication of that model of infrastructure is if you want microservices teams, you end up having those microservices teams having to write Puppet code and care about the infrastructure layer, which is not really the application domain so much. It's more plumbing and wiring together of services rather than dealing with the application level problems.
The problem space is much bigger, right? It's not only do an individual microservice needs to be configured from all the way from the kernel up to the application layer, but your entire platform as you grow, at that point we had probably 40 services we were running. So that's 40 things that are configured in different ways and have slightly different tuning characteristics. So it's not possible for there to be a single team doing support that can do that effectively. The problem space is too big. And then if you split the problem up and devolve the management of those services to multiple teams, as we've done, that's fine, but then each team needs to understand the top to bottom problem space. And that makes scaling the teams difficult because you have to put all those skill sets into every team, and every team has to solve those problems over and over. And it's hard to do, right? So here, again, we're talking about these role-based provisioning tools, which, I mean, don't get me wrong, I love Puppet. I've been using it for ages. It's wonderful. But we're kind of we're making people solve problems that should be straightforward, right? We have to, how do we deploy this API service again? What services need firewall access to the message queue? What port does Rabbit listen on, right? These are the wrong problems for us to solve. Our customers don't care about firewall rules. Our customers don't care about the size of our VM. They care about the application that they're buying from us to make their video platform great. And that means the more time we spend thinking about provisioning instances or writing firewall rules, we're wasting time that we could be writing great applications for our customers. So we need to change it so that the teams are thinking in terms of applications and not in terms of machines or infrastructure.
Yeah, so that's the value proposition that a cluster manager brings. It means that application developers are working against an API that is basically at a resource pool level, rather than VMs, provisioning, Puppet, etc. A developer is working at a much higher abstraction when they're doing their provisioning, and that is how many CPUs do I need to provision, how much RAM do I need to provision, how much disk capacity do I need to provision, etc., etc. They're thinking about the resource constraints that they need to have their application run, not necessarily where that application is going to run in the infrastructure. So that's the real value proposition of moving away from something like Puppet to a resource cluster scheduler like Mesos.
And so remember earlier we talked about not wanting to pack many services onto the same machine, and now we're kind of making the argument that you should. That seems a little backwards, but it's because these cluster managers can offer that resource isolation guarantee that we don't have out of the box from the operating system. All of them, Docker, Mesos, Yarn, Kubernetes, they use the Linux cgroups technology to make guarantees about how much of a slice of CPU a given task can have, how much RAM it has access to. And this gives us the guarantees that we need to be able to safely co-locate many applications onto the same virtual machine and then spread our load around much more efficiently. And so we found our first happy secondary side effect. And this was the problem space for the application management suddenly shrunk. Whereas before, 2.5 years ago, when we started moving into the Spark space and we needed Yarn clusters to run our Spark streaming applications, getting it going was a combined effort between the development team that had an application that needed to run and somebody with some system skills who understood the AWS APIs, understood config management. Together they could build an EMR cluster and get some Puppet code on there to configure it for us and figure out how to deploy their application and iterate and get it finally ready for production. That was several weeks of work usually. So let me tell you about a guy named Dave. Last week, Dave was developing some new Flink applications. Flink runs in a session, and it manages a bunch of task managers. It's a little mini cluster. And he realized that the application he was developing had a different purpose to the other Flink applications running on our current Flink session. So he thought, let me make a new Flink session for this. That seems like the right thing to do. He wrote some JSON, threw it at the cluster, and had a new Flink session that he could deploy his application to. The effort involved went from elapsed time of weeks to elapsed time of about 30 minutes. This is transformative, right? If you can come along and ask for a new big data transformation cluster in 30 minutes, what can you do? So this is how we started thinking this way. We started with Spark for a lot of analytics work. We started moving into the Flink space about a year ago. And both of these, at the time we were looking at Flink and Spark, neither of them had support for cluster frameworks other than Yarn, particularly. And Yarn's it's a natural choice, right? EMR is on AWS, we're on AWS. It's straightforward to get going on. And it gave us the experience of running large workloads on clusters of machines and made us start thinking about our workloads in terms of isolated containers that were co-located potentially on the same machine but with resource isolation guarantees. So it started pushing our thinking into what else can we model this way? What else is going to be possible?
Yeah, so we dipped our toe into the cluster pool, and because we were thinking about batch applications predominantly, we started off actually with looking at Yarn. Yarn was like a lowest common denominator. It was spun out of the Hadoop world, and we were looking at batch applications. So the first things we span up were Yarn and Flink, and Flink at the time only supported Yarn. So we ended up with a Yarn cluster. But then later, when we started looking at and started seeing the benefits really of this kind of model of cluster management, we looked more at Mesos, and we started thinking about how we run long-running services as well, in addition to our batch workloads, and that's what made us look at more deeply at Mesos. Yeah.
So, I mean, we started small, right? Push our API services into Docker containers, and then start looking at cluster schedulers. And I mean, there's an awful lot out there. It's a big space. We settled on Mesos because we think it solves some problems for us. Your decisions might be different. If you don't have big data needs, you might look at something like Kubernetes because in a lot of ways, it's easier to get going for API services, but we were thinking that in the long run, we'd be combining these clustered technologies. So this is a screenshot of the Marathon UI. Marathon is a framework that runs on top of Mesos and allows you to easily schedule workloads to the Mesos cluster. Compare this to when we had the slide of our AWS utilization that was 500 machines, 150 CPUs for API services. This is the same 150 API services running on our Mesos cluster, and it now uses 50 CPUs. So we've cut our spend, right? We've just saved ourselves 60% of our AWS bill for API services. So that was what we wanted to do, and that worked. This is the Mesos UI. It's a read-only view of running tasks on the cluster. And this is another happy secondary side effect. These are heterogeneous API services running on the same cluster. So at the top, there's a Java application, then there's some Node.js applications, and there's a Python application. But from my point of view, of someone who looks after the estate, my problem space is reduced. I have to care about Mesos. All the team has to care about is how do you shove that Java application into a container, and then it can deploy the same way as everything else. Same for the Node.js, same for the Python. The problem space is suddenly reduced, and it makes our management of the cluster much easier. But we still had other types of clusters out there, right? So this is the Yarn application overview for some of our running Flink sessions. It's a very noisy dashboard, but what you can see is it's a Flink session with 8 task managers. There's 7 containers. They're using this much memory, and it's our application that provides us the thing we actually care about, and that's running on top of Flink, which is running on top of Yarn, which is running on top of Hadoop, which is running on top of EC2 instances. And each of these layers has about 12,000 configuration knobs. And so this is we still have a lot of complexity, a lot of moving parts. And this is right alongside our now also running Mesos cluster. So also, each cluster is single purpose, right? So we have our Java batch big data clusters on Yarn. We have our API services on Mesos. And it's hard to scale efficiently. Each cluster has overheads. So Mesos needs some master nodes, some zookeeper nodes. Yarn needs resource managers, and so on. The people looking after it have to be familiar with all of this. You know, the 12,000 knobs per layer adds up, right? That's a lot to keep in your head and to know where to look at 3 in the morning when something blows up. And our bin packing still isn't as good as it could be. There's waste in each cluster, and you have to leave some room in each cluster so that the application can respond to load events. So we're starting to look now at how we could make this better, more efficient, and easier to run. Again, go ahead.
Yeah, so where we wanted to get to really is a single platform for deploying all application types. We want development teams not to have to care about the underlying infrastructure at the machine level, just to care basically about the applications they're running and the constraints that they want those applications to run within. And we want application developers to think declaratively about what they want to deploy, rather than writing Puppet code to get it deployed. We want them to declaratively say, I want this much CPU, this Docker container, and these constraints, and let the cluster manager sort it all out.
So this is, I think, our next iteration on this. We have a single platform, and we're starting to look at not just heterogeneous API services, but heterogeneous workloads. So what you can see here, again, this is the Mesos UI view. At the top, there's an API service written in Node.js. And the middle line is actually a Flink session, also being run by Marathon. Marathon provides us guarantees about restarting tasks in case of failure and ensuring that N copies are running on the cluster and so on. So we're using Marathon to run the Flink session to give us that HA, but Flink is itself then connecting back to Mesos and requesting task managers and managing the application workload that way. So we're starting to now, we have a streaming application running alongside of our API services on the same cluster. But
so if you're thinking about making a move to Mesos, you really need to look and deconstruct the applications that you want to run on Mesos and think about the different workload types that you want to be performed on top of that cluster. And if we look at our video platform, we have API services. These are customer-facing, the business service-critical services, and we want them to be, obviously they're long-running, but they're critical applications. Behind that, we have our database layer. We have Kafka as a sort of central nervous system behind, with stream processors processing data as it arrives from our API services and other application and other interactions with the database. And then behind that, we have cron jobs doing scheduled tasks such as backups, report generation, that kind of thing. And then finally, because we're a video platform, we do transcoding. So we have a set of batch transcode operations that we're doing for our customers, and a variety of other different types of batch applications as well. But the important thing is we have 3 major different categories of workload types: long-running services, batch services, and scheduled tasks. The scheduled tasks and the batch are kind of similar, but they're sort of less critical background operations. We want these 3 different types to be all executed on Mesos, basically. That's the end game, because that gives us a single small surface area for our deployment, and it's consistent against the different workload types. The important thing to be aware of with Mesos is that it's not a complete solution for deploying applications. It's more akin to kind of an operating system kernel. It gives you an interface into the resources that are available, but you still need an application on top of that to do actual work. Mesos requires an application on top of it to do the actual work, and in the Mesos world, that's called a framework.
Yeah.
And
with this kernel metaphor, Mesos knows how to run a task but won't do it itself. So we need, on top of Mesos, we need the equivalent of an init system, a shell, a cron daemon, something that requests that workload from our kernel.
So if we look at Mesos and the framework interaction, we have user on the right-hand side here. They submit their JSON, their declarative description of the work that they want to perform. That gets queued or put into some sort of background queue. And then that framework listens to Mesos, which is providing it with resource offers. And these offers are, hey, I've got a VM over here which has got a certain number of CPUs available. Is that suitable for your application? And the framework might say yes or no. It might decide to decline that resource offer. Or it might choose to accept it. If it accepts it, it will send a task back to Mesos, and then Mesos will do the actual work to deploy that application and actually run it, subject to the task definition that has been supplied. So yeah, this distinction between Mesos as the kind of kernel and then a set of applications running on top means that you've got a really powerful abstraction for scheduling work into Mesos.
I just want to point out, this model is kind of upside down from Yarn or Kubernetes or many of the other cluster schedulers out there. In those, you ask the cluster, can I have 8 CPUs and 32 gigs of RAM? And the cluster just says yes or no. By remodeling it so that Mesos is making you an offer and you're deciding to accept all or part of it or none of it, you can make really interesting topologies and you can make runtime decisions. So Netflix has a library named Fenzo that you can use to plug into your framework and make more complicated decisions. You can actually describe topologies like, I'd like all my API services to be evenly spread across my data centers, but for my batch work, I'd like them all to happen in rack A and data center A, except if rack A is full, and then it's okay to spill over into any other rack in data center A. That's really hard to describe to most cluster frameworks, but because of this resource offer, you can evaluate each offer and say, well, nothing else is coming in for rack A, I'll start accepting offers in rack B. So
yeah, so basically hard and soft constraints is what that boils down to. And Mesos, what this has resulted in is a lot of different frameworks that you can choose to execute your work on Mesos. Some of them are very narrow in their scope. Some of them just run a particular application type. So the Kafka Mesos framework just runs Kafka, similarly with Spark or Storm. But then there are more general purpose frameworks for running workload types that are specific to that workload type. For example, Marathon, it just runs long-running long-running services basically. And then Chronos is another example, and that's just running background scheduled tasks. So you have a wide variety of different choices you can select for your different application and workload types. The real outlier from this selection here is in the top left, and that's Aurora. That's a far broader and more general purpose framework on Mesos, and that's one that we're going to be focusing on really for the rest of the talk. The big 3 frameworks out there on top of Mesos are Marathon and Chronos and Aurora. Marathon for long-running services, Chronos for the batch services. Aurora can do almost everything, but it's a little bit harder to deploy, to maintain, and to actually work with. But the amount of power that you get from it, if your workload characteristics and your requirements are suitable for Aurora, then it's a fantastic choice. So I would say if you have the need for running batch jobs like directed acyclic graphs of batch work in your cluster, then Aurora is a good choice. And if you need preemption, so if you need to have the ability to cancel work because higher priority work is coming into your framework, into your scheduler, and you want to cancel that work, then Aurora is another framework, is a framework that can provide that. So it's really a holistic solution to workload scheduling. So do you have a large engineering team and you want to provide different spaces within your cluster for those teams to provision work themselves? Or do you have multiple isolated customers that need quotas and that kind of thing? Because Aurora provides quota management and preemption, which allows you to dedicate resources to particular users. Aurora came out of Twitter, and their vision for Aurora was to have the entire engineering team at Twitter running on top of Mesos and Aurora. So they wanted their development team to be able to do experimental deployments or staging deployments or even production deployments all on the same framework. So it's not just, it's a far broader set of requirements that we're aiming to achieve with Aurora. And yeah, so it's the noisy neighbor problem. With the other frameworks, one user can provision work in the cluster that can consume and saturate all of the available resources. That's a problem because you want to have each user of your cluster able to do critical work, but also be able to, you want some management across critical work and to be able to ensure that high priority work is scheduled, but also make space for lower priority work to get done if the capacity is available.
So you remember earlier we said, Docker and Mesos offer resource isolation using C groups. So that gives us the isolation we need at the task layer, but this gives us the isolation at the cluster layer. So even though I know that my task once run will get enough CPU to do its job, this gives me the ability to say I can have 500 tasks. That's my share of the cluster. But if Dave comes along, he can still have some more tasks as well. So this is the business case, right? Not every customer, it's not a fair queuing system or something, or a FIFO. Some customers pay us more money. Some customers have higher priority work. We have different SLAs for different customers. This one might need to turn around in minutes, and this one is prepared to wait days. So we need to be able to prioritize their work and have an underlying platform that makes those guarantees to us so that we can make the guarantees to the customers about this. So, yeah.
Yeah, so Aurora has a concept of a role, and a role is like a user in Linux, basically. It's a name with a set of permissions assigned to it, but also the ability to assign quota limits in terms of CPU, disk, and memory to that role for its production work. And this is what allows us to dedicate resources to individual users. So the real goal and the real advantage for us as a video platform provider is that we want to make sure that high priority work gets done. So even though we might have low priority batch work going on in the background, we want to make sure that if we need to scale our API services, there's some really popular TV show that's airing, and we want to make sure we've got the API services scaled up. We need to make sure that high priority scaling can occur, even though we have low priority background batch and cron work going on in the background. And different customers are executing their workloads on our cluster. We want to make sure that we can provide guaranteed resources to those workloads for those customers. And that's achieved by quota and quota isolation for roles. If there's no high priority work ongoing, we want to make sure that the low priority work can consume all the resources, but if high priority work comes along, we want to make sure that we can deprovision, preempt existing work to make way for the high priority work. So preemption, the killing and rescheduling of low priority work in favor of high priority work, will happen in Aurora under two conditions. Within a role, you can have a customer have a lot of low priority work that's executing, and then later they can submit something that's higher priority, and Aurora will kill one of the low priority jobs or services or whatever to make way for the high priority service. So we've got prioritization within the role. The other type of preemption that Aurora supports is across roles. So if you have a set of low priority work that's going on across roles, but then a user requires that they've got quota to submit some high priority work, it can decommission another customer's work or another user's work to make way for that high priority job, for example. So this allows us to partition up our cluster in terms of roles or users. So we can have a production side where we have a certain number of CPU allocations for customer A, customer B, and then we have non-production work where we don't have any quota assignment and we can just preempt and steal that work to make way for our high priority production work.
So this is it happening, right?
Yeah.
We launched a low priority task. Within 2 seconds it was running, and it ran for 4 minutes until that resource was needed by a higher priority task, at which point the low priority task was killed, the high priority task used that resource, and then 10 minutes later, the low priority task was resumed once the cluster had resource and finally ran to completion. So this is the guarantee we need to make. We can use the cluster resource when we have load events or we have some other need for high priority work to progress immediately, but the low priority work still has to get done. Their customer still wants to see their video at the end of the day, right?
So the net effect of the prioritization and preemption model that Aurora supports is we can have a set of high priority work that's ongoing and guaranteed, but we can fit low priority background tasks around it. No other framework supports that model of cluster management like Aurora does. So if you need quotas and you want to really make use of a large cluster efficiently, then Aurora is a really good choice.
Again, we're going back to the bin packing thing we talked about earlier. So we can provision our cluster to run our API services with some headroom for load events, and then use that headroom. So we get as efficient bin packing as we can out of the technologies we're using. So there are some, this isn't a magic bullet, right? There's always some things that aren't perfect.
Yeah, so one of our workload types that we've mentioned already is Apache Flink. And Flink is like a mini cluster for running batch and stream applications. And it has built in its own Mesos scheduler that will go off and provision and scale up and scale down task managers to do the stream processing work. But there's no first-class support in Flink to interact with Aurora to provision that work, so we have to provision it directly on top of Mesos. So the result of that is we can provision the Flink job manager, the central component in Flink, on top of Aurora as a kind of long-running service. But when it needs to scale up itself, it needs to communicate directly with Mesos, which means that we don't have that quota isolation. We don't have some of the benefits that Aurora is bringing, so we can't fully commit to this role-based, isolated model that we would like to commit to.
Yeah, we basically have some work that is invisible to the quota system.
Yeah.
So for us, this is fine. And for probably most of you, this is fine. But it's something to be aware of, that it doesn't just disappear by deploying this stuff.
Yeah, so our stream processing applications are not subject to the quota constraints of Aurora. So what you're likely to end up with if you go down the Aurora routes, particularly at the moment, is Mesos with Aurora on top, a set of customers with their quotas, but then a set of other frameworks on the side of Aurora, such as Flink or Spark or Kafka, which are provisioning their own resources for themselves directly to Mesos.
So
yeah, that's cool.
Yeah, this is where we are. We're running a Mesos cluster. We're running most of the API services on Marathon right now because it's very simple. It's a JSON API. It's a battle-tested solution. It brings an awful lot to us, but we're starting to run more of our customer work on Aurora, and we're probably looking to move our API work over to Aurora to simplify our deployment story. We're still running Flink, Spark, Kafka alongside this. Again, this work is invisible to Aurora, but for the moment, that architecture is suiting us fairly well. But plenty more interesting work to do to make for the unified cluster story we want.
Yeah, like as was said in the keynote, I think every company sponsoring is hiring, and we are no exception. So if you're interested in some of the topics we've been discussing, working with container schedulers, that kind of thing, working on the video on a video platform, then yeah, come and speak to us after, and we can have a conversation.
And if you have any questions now and you aren't looking for a job, I'm sorry, but feel free to ask the question.
Do you have any questions? Come on.
Okay.
No one? Well, they will be over here. So thank you very much.